Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss controlling hydronic heating systems. To cover today's topic, we have Trane application engineers Scott Delo, Sarah Hilden, and Ben Sykora. Ben is going to get us started. So Ben, what's different about this program, and why are we discussing controls again?
Sure, Jeannie. HVAC controls have evolved from thermostats and pneumatic actuators to sophisticated digital systems. A typical system now includes a local controller on each piece of equipment and a higher-level system controller that stages equipment on and off, manages set points, schedules, occupancy modes, and more. A recent Engineers Newsletter Live covered ASHRAE Guideline 36, Sequences for High-Performance HVAC Systems. Another recent ENL covered control strategies for air-to-water heat pumps and storage source heat pumps. So why are we here again talking about HVAC controls? The short answer is that electrified heating systems are evolving rapidly, and many engineers are running into similar challenges when designing electrified heating systems. Today, we will be talking about how to control heat recovery units, including the impact of different piping arrangements. We'll consider operational differences between centrifugal and positive displacement compressors for heating applications. Then, we'll talk about how to control chilled water and hot water temperature at the same time with a dual condenser heat recovery chiller. Next, we'll explore nuances associated with different sources of heat, including everyone's favorite topic, defrost operation in air-to-water heat pumps. Finally, we'll explain how to use modular multi-pipe units as a simple and effective way to regulate both chilled water and hot water temperature. But before we jump into those topics, let's back up and think about the fundamental requirements to control any piece of HVAC equipment. The purpose of any control system is to regulate a desired condition, whether it's air temperature, fluid temperature, pressure, or anything else. Regardless of which type of control is used, there are four key elements that must be included. First, we must decide which characteristic is being controlled and what the desired value is. Let's call that the set point. Second, there must be a way to measure that characteristic, whether through direct measurement, such as a sensor, or with indirect estimation. Next, the system must include a means by which to take action. This may include adjusting a valve position or changing the speed of a pump. Finally, the controller compares the measured value to the set point and determines which actions to take. If any of these four elements is missing, then it will not be possible to regulate the system operation. Likewise, the performance of the system is directly related to the performance of these four items. For the rest of this program, we will use this table to identify control requirements for various systems. Let's start out by examining pump control for a modular heat pump. Later, we'll analyze other aspects of modular heat pumps, but for now, let's focus on maintaining enough DP that the heat pump flow requirement is met. The set point for this system is differential pressure at the heat pump inlet and outlet pipes. A differential pressure sensor is installed at the fluid pipes near the heat pump. The action device is the variable speed drive on the pump. When a controller detects the mismatch between set point value and measured value, it adjusts the speed command to the variable speed pump until set point value is achieved. Before moving on, let's do a thought experiment on this system. What would happen if the DP sensor is out of calibration, reporting a value that is 20% higher than the actual value? When the controller sees the higher pressure reported by the sensor, it reduces pump speed command. The pump slows down to maintain DP set point. That 20% sensor error has resulted in a 20% error in the system operation. Selecting high-quality sensors and maintaining their calibration has a direct impact on system operation. Next, let's consider hot water temperature control with a centrifugal heat pump chiller. For this example, the leaving condenser fluid temperature must be regulated at a hot water set point value. A temperature sensor is installed in the condenser leaving fluid pipe. The action device is heat pump condenser capacity. For centrifugal compressors, capacity is adjusted with inlet guide vane position. The unit controller adjusts capacity as needed to achieve hot water set point value. The first question that you might ask is, what about chilled water temperature? As the unit controller adjusts capacity to maintain hot water temperature, the evaporator capacity also changes. This is one of the fundamental challenges that we'll address today. How do you design a system that can control hot water temperature and chilled water temperature at the same time? Spoiler alert, we're going to add a second controller and a second action device to regulate that second set point. Another common question is, hey, what about adjusting compressor speed with a VFD? If the heat pump includes variable speed drive, then the unit controller has two action devices and must coordinate between the two. For centrifugal compressors, the VFD speed is based more on lift than it is on load. Sarah, could you take us through some examples of heat recovery control?
Sure. Thanks for the introduction, Ben. To start, let's define the baseline system. This is what we'll compare against as we demonstrate the increase in system efficiency through system configuration decisions. Our baseline system has variable primary flow chilled water in blue. These are water-cooled chillers, so the upper salmon-colored lines represent the condenser loop. Only one tower is depicted in the diagram. A Sidestream heat recovery machine is piped into the chilled water return. The hot fluid supply is decoupled from the distribution. Notice, this fluid is hotter than the condenser loop, so the supply is a deeper shade. Last, the inclusion of the heat exchanger loop is to reject excess heat to the cooling tower from the heat recovery chiller. Later on, we'll consider preferential loading and discuss equipment sizing and selection considerations with a focus on the impact on overall system efficiency through specific choices made in design. But for now, let's discuss the system diagram in a bit more detail. The system design cooling load is 1,200 tons at a 16 degree Fahrenheit delta T. It includes two cooling-only chillers, sized a bit less than half the design load. A smaller heat recovery chiller, sized for the coincident heating and cooling loads, is piped into the Sidestream position. The cooling-only chillers in a variable primary flow system are selected for the design flow rate at a reduced delta T. This is because their return fluid temperature is slightly lowered during heat recovery operation. There are two chillers, and the system requires 1,800 GPM. So chillers and pumps are selected at 900 GPM. Redundancy is not considered in this example. Heat rejection for the cooling-only chillers is in the form of an open cooling tower. Moving into the heating loop, chillers operating in heat recovery mode may be capable of controlling to either leaving evaporator or to leaving condenser temperature. Because both hot and cold fluid pumps on the heat recovery chiller are constant speed, as the heating load decreases, the leaving evaporator temperature rises. And that's okay, because we have the other cooling-only chillers to take the cold fluid the rest of the way. An important point, if the heat recovery unit is the only unit operating to satisfy a cooling load, but the heating load is low, the heat exchanger pump is enabled to reject additional heat to the towers. We'll talk more on this later. I just mentioned that heat recovery chillers can be controlled to either the chilled or hot fluid temperature. Depending on system requirements, one or the other may make more sense. Control the leaving chilled water temperature when heating loads are light and don't require tight temperature control. A heat recovery chiller piped in the preferential position has to make the leaving chilled water set point. Otherwise, mixing results in an elevated supply temperature. This might be okay under light cooling loads. However, if the chiller serves a process cooling load, cold fluid temperature is likely critical. Knowing how far the unit needs to unload is important, especially for centrifugal units. Understanding the load profile is key in this regard. Logic may be put in place to enable these units only under loads adequate to avoid the surge region. When heating is a priority, like in the middle of winter, it makes sense to control to a hot fluid temperature. With Sidestream heat recovery, the heat recovery chiller evaporator is piped into the chilled water return. This saves energy because its leaving evaporator temperature can float upward, resulting in reduced lift. Of course, process heating loads often have stringent temperature requirements, and domestic hot water should be served or held above a certain temperature. Give proper care and consideration during design to identify appropriate control for the given application. Now, let's tie back to what Ben stated earlier about hot water supply temperature control. With the heat recovery condenser in the Sidestream position, there are two things being controlled: the hot water supply temperature and the distribution pump speed. Hot water temperature control is handled by the unit. The set point is the supply hot water temperature, 115 degrees here, measured at a sensor inside or at the outlet of the chiller. Capacity control depends on the type of chiller, but is handled within the chiller's unit controller. The system controller needs only to provide a hot water set point. Distribution pump speed must also be controlled. The differential pressure measurement is compared against the current differential pressure set point. The pump controller reduces pump speed as system valves close down because the system pressure increases above the set point. They'll speed back up when valves open, asking for more flow to maintain that differential pressure set point. Next, let's look at a part load scenario. At a point in time, the system heating load is 2,000 MBH and 550 cooling tons. Just one cooling-only chiller is required. The heat recovery chiller controls its leaving condenser fluid temperature at 115 degrees. The heating coil loads went down, so they don't need full flow, and the distribution pump slows down. The primary condenser pump, however, is constant speed, so there's some excess flow in the heating bypass, and the condenser return temperature increases to 103 degrees. What happens on the cold side? The heat recovery unit's leaving evaporator temperature is 43.2 degrees. However, it's a larger share of return. So the return temperature into the cooling-only chiller is reduced to 52.3 degrees. The heat recovery chiller is producing the 2,000 MBH of heating it was asked for, but only produces 128 cooling tons, with the remaining 422 tons handled by the cooling-only chiller. Because the cooling-only chiller sees a lower return temperature, it operates efficiently, and part of the cooling load is reused to satisfy the heating loads. It's an efficiency win, and the control is as described, simple and reliable. If the cooling load drops low enough, it may be satisfied by operating only the heat recovery unit. This may be desirable in systems with large cooling-only chillers incapable of significant capacity reduction. Alternatively, if the building owner is concerned with emissions and the backup heat source is gas, they may prefer to operate the heat recovery unit. Let's assume the cooling load is just 130 tons, and the current heating demand is 1,700 MBH. And we continue with the current deployment of leaving condenser temperature control at the heat recovery chiller. What happens? The heat recovery chiller produces the required 1,700 MBH at 115 degrees. However, its evaporator can only meet 109 tons at 240 GPM. Accordingly, the chilled water supply temperature is not met, and a cooling-only chiller is enabled at an inefficient load point. This is certainly less than ideal. If instead we allow the heat recovery chiller to control to its leaving evaporator temperature of 40 degrees Fahrenheit, the cooling load is met by the heat recovery chiller alone. The primary chilled water pump is required to pump the distribution loop. Because the constant speed heat recovery unit's evaporator pump produces 240 GPM, some chilled fluid mixes with the system return, reducing the return seen by the chiller to 53 degrees. This unit is able to fully satisfy the cooling load at the design supply temperature. However, the condenser leaving temperature increases, and there's 330 MBH of additional heat to reject. The heat exchanger loop is engaged to reject this excess heat along with the cooling tower and its pumps. Control of the heat rejected is based on the return temperature into the heat recovery unit's condenser. Under low load conditions, the return temperature rises, in this case, to almost 105 degrees. The heat exchanger pump speed is modulated based upon that return temperature. We can reject more heat as needed when the return temperature increases by increasing the pump speed, and vice versa. Through the addition of system-level control, both the heating and cooling demands can be met. A chiller bypass around the cooling-only chillers could be added, increasing cost and transition complexity. Today's chillers often permit cold water flow through the evaporator while disabled. Another way to pipe in a heat recovery unit is in the preferential position. When configured in this fashion, the heat recovery chiller is required to meet the leaving chilled water set point to ensure the system receives its design fluid temperature. Let's consider an intermediate stage, a single cooling-only chiller operating together with the heat recovery unit under moderate load. Variable condenser flow can be implemented to maintain the hot fluid temperature set point. The condenser supply pump is equipped with a variable frequency drive to control flow, or a valve could be used. But in either case, there must be some mechanism to ensure condenser flow is not reduced below the manufacturer's specified minimum flow rate. As the cooling load increases, without flow modulation, the leaving condenser temperature necessarily increases. Increase the pump speed to reduce the leaving heating temperature to avoid additional heat rejection. Let's wrap this section up. To ensure project success, take care to think through the control points required to achieve design intent. Sidestream heat recovery control is simple and adapts well to changing load conditions. Depending on the application requirements, preferentially loading heat recovery chillers may be suitable. And there are bound to be several operating modes based on system needs at a given point in time. Take time to think through which equipment operates during each mode and associated component control required. Pumps may have sizing dependencies related to different operating modes, and chiller selections vary based on system configuration. And a final note on sizing. Without a full year load profile for both heating and cooling, it's difficult to right-size the heat recovery unit. You want it to run as much as possible to increase overall system efficiency. But if it's too large, especially for centrifugal chillers, it may not have adequate turndown under low loads, or it'll be underutilized. Use an energy modeling tool like Trace 3D Plus to model new buildings. For replacement jobs, trend plant or coil load data to fully understand the sizing implications. Consideration of the points shown lends to successful project implementation. Now that we've covered our baseline system and pertinent control points, I'm going to turn it over to Scott to discuss chiller technology combinations that can benefit these types of projects.
Thank you, Sarah. In most comfort heating applications, there are only a handful of hours when the plant heating load is at or near the design capacity. Most of the heating hours are spent well below the peak. This graph shows the comfort heating load for a building sorted from largest to smallest. The horizontal orange line shows the average annual heating load. In this building, the average load is approximately 1/8 of the design peak. While not every load profile is identical to this one, it illustrates why heating system turndown is important regardless of plant design or equipment type. Before we look at a few plant layouts, let's start by reviewing compressor types and how they unload. First, let's look at centrifugal compressors, often used in medium to large chilled and hot water systems. For any heat pump or chiller, lift is defined as the pressure difference between the evaporator and condenser. This pressure difference can be represented as a temperature difference by subtracting the evaporator leaving temperature from the condenser leaving temperature. Centrifugal compressors create that pressure difference aerodynamically, similar to how fans create differential pressure. The compressor's behavior closely follows the fan affinity laws. Let's focus on fan affinity law number 2. In practice, compressor speed is a function of both load and lift. The compressor must spin fast enough to meet both the required lift and to move enough refrigerant to meet the load. The differential pressure created by the compressor is proportional to the change in speed squared. As a result of this relationship, lift changes rapidly when compressor speed decreases. In most heat recovery and heat pump applications, lift must be maintained to meet the design hot water and chilled water supply temperatures. Depending on the unit, this may limit centrifugal chiller unloading characteristics. Always verify unit turndown with the manufacturer at the intended operating temperatures. Let's compare how positive displacement compressors differ from centrifugal. Positive displacement compressor lift is determined by their design compression ratio. In scroll compressors, it would be the ratio of volume at the intake port divided by the volume at the discharge. Reciprocating and helical rotary compressors are also designed for a specific compression ratio. To unload, compressors can be cycled on and off, speed varied, or in the case of helical rotary compressors, a slide valve can be used. Unlike centrifugal compressors, positive displacement unit lift is not impacted as significantly by the percentage of load. Positive displacement compressors typically have better turndown, especially under high lift. For this reason, it's often advantageous to pair centrifugal compressor units and positive displacement units in heat pump plants. Let's look at an example. In this example, we have two 1,000-ton centrifugal cooling-only chillers. To reduce building natural gas usage and operating cost, it's decided that a heat recovery chiller shall be added to the plant. The peak simultaneous cooling and heating load is determined to be 250 tons. The heat recovery chiller is placed in the Sidestream position. As Sarah covered, this simplifies control by allowing the heat recovery chiller to control to condenser leaving temperature and letting its chilled water temperature float. At full load, the heat recovery chiller must make the design 40-degree chilled water temperature while making a condenser leaving temperature of 130 degrees. At reduced load, the Sidestream unit benefits from slightly reduced lift. Heat pump chillers should normally be selected to unload down to 25% load or lower if possible. Selecting a centrifugal heat recovery chiller that can unload this far may be challenging. So what can designers do to deal with these limited unloading capabilities? Let's say that the selected heat recovery unit can only unload down to 65%. Since the unit is in the Sidestream position, it can be easily controlled to meet the hot water supply temperature. Unfortunately, if the hot water load is less than 65% of the unit's capacity, the heat recovery chiller will have to cycle on and off to meet the load. Given the large number of hours in a typical comfort heating application that are well below 65% of capacity, this unit will be subjected to excessive starts and stops, shortening the unit's operating life. Let's look at how changing the heat recovery chiller to a positive displacement unit improves plant operation. Changing to a helical rotary positive displacement heat recovery chiller increases the unit turn down to roughly 25%, an improvement over the centrifugal chiller. The rotary chiller is also controlled to the condenser leaving temperature, and most importantly, the unit is able to run most hours without cycling. If more turn down is required, another solution would be to switch to two smaller 125-ton heat recovery chillers. Next, let's look at another example. In this example, we have one 1,000-ton cooling-only chiller paired with two 500-ton heat recovery chillers. The design conditions are 40-degree chilled water supply temperature and 115-degree hot water supply temperature. Since the simultaneous heat recovery load is large and equal to the cooling-only capacity, it's determined that preferential loading rather than Sidestream would be best. Since the heat recovery chillers are located in the preferential position, they must be controlled to leaving chilled water temperature in order to maintain plant supply temperature. Since the primary pumps are constant flow and leaving water temperature set point is fixed at 40 degrees, the unit load is a function of return water temperature and therefore nearly constant if the system maintains delta T. As a result, the plant will not allow the chiller to unload, even to the 60% stated on the submittal. If the heating load is less than one heat recovery chiller, when the first machine runs, it will eventually overshoot the hot water supply temperature and force the unit to cycle off. The same thing will happen if the heating load is between 500 and 1,000 evaporator tons. So what can be done to improve the plant's ability to match the load? In order to improve the plant's ability to match the heating and cooling loads, two positive displacement heat recovery chillers are added on the opposite side of the bypass. Each 250-ton heat recovery chiller is able to turn down to 25% of its load, which is 6.25% of the heat recovery capacity. Their location in the plant is not preferentially loaded, and therefore they can unload all the way to their stated minimum. The helical rotary chillers can be used as swing chillers to match the required load, meaning they should be the first and second chillers added. Once their capacity is exceeded, there's enough load to start the 500-ton centrifugal heat recovery chiller. This ensures that the 500-ton centrifugal will not exceed the required heating load. This makes the control much simpler. When the 500-ton chiller is started, more flow will move through the bypass, unloading the helical rotary machines so they can be subtracted and turned off until the load increases. As you can see, this greatly improves the plant's ability to match loads. Combining centrifugal heat pumps with positive displacement units enhances the plant operation. Centrifugal units are typically larger and more efficient, but may be limited in turndown, especially under high lift. Positive displacement units have the turndown that centrifugal units often lack. Combining the two creates an optimal plant when designed properly. In order to see the benefit, the centrifugal unit needs to be preferentially loaded. Look for the bypass. If the bypass is between the heat pump types and the centrifugal unit is closer to the load, it's laid out properly. This is true for both preferential position as well as Sidestream. Back to you, Sarah.
Any chiller can recover heat by using fluid heated in the condenser for a useful purpose. The great news is there are other options available. A standard condenser chiller is what we're all used to. It includes a single condenser with two pipes, one in and one out of the condenser. A dual condenser has two condenser shells. One rejects excess heat not needed by the system or during cooling-only periods. The other is dedicated to heat recovery. With multiple condensers comes another set of pipes. These are often referred to as 6-pipe units. This may be a full-size condenser with capacity similar to that of the standard heat rejection condenser, possibly designed for higher leaving fluid temperatures. A split condenser is one in which both condensers are contained within a single shell, separated by a metal plate. Refrigerant moves freely, but fluid streams are separate. Now that we know what the options are, let's talk through some applications. Let's preview the basic system before going into detail. A dual condenser heat recovery chiller produces hot fluid inside its heat recovery condenser. Its evaporator is piped into the chilled water return in the Sidestream position. Its standard condenser is connected to an open tower. The tower also serves other cooling-only chillers in the system, which are not shown. The heat recovery condenser serves heating loads. These loads require warmer fluid than needed for heat rejection, hence the deeper color. In the event the system needs heating without a cooling load to source the chiller, auxiliary heat is provided in the hot supply fluid stream. The dual condenser unit includes two pipes for chilled water. Two for the heat recovery condenser, which is the upper heat exchanger, and two for the standard condenser in the middle. Flow through the standard condenser determines the heat recovery condenser capacity. The set point is leaving condenser temperature, controlled by the heat recovery controller. As the hot fluid temperature drops, a three-way valve diverts flow to the tower. Flow through the heat recovery condenser is reduced, increasing its leaving temperature. It's important that this valve has good authority to ensure stable and precise control. A butterfly valve should not be used here. In this configuration, the flow rate over the tower cells is constant. Because the heat recovery chiller has two condensers, it is possible to reduce flow beyond the standard condenser minimum because heat is being recovered in the other. Below this flow rate, control stability may be degraded. Ensure minimum flow rate is maintained in at least one condenser shell. Another option is to directly modulate the standard condenser flow. Using a modulating valve on the standard condenser enables variable flow through both the standard condenser and the cooling tower. As in the last case, select this valve with good authority for more precise control. Control is like what we saw in the last slide, but in this case, flow is not diverted to the tower. Take care to ensure the minimum flow rate through either the cooling tower or the cooling-only chiller condensers is maintained. The flow can be measured directly, or a differential pressure measurement across the condenser can be used as an analog. Now, one last configuration. Series chillers are common when the chilled water system is designed with a high delta T. In this configuration, the upstream chiller is equipped with a heat recovery condenser to enable reuse of otherwise wasted heat energy. Aside from the obvious heat recovery benefit, fewer ancillaries need to operate, saving even more energy. We just discussed methods to balance the heat being rejected with that being supplied to the heating loads. Applied to this case, the heat recovery chiller is controlled to its leaving heat recovery condenser temperature, which means its leaving chilled water temperature floats with the heating load. The downstream chiller operates to the system supply chilled water temperature. But we may need more cooling than the downstream unit can provide. In that case, the heat recovery chiller needs to meet more of the cooling load. Control of the heat recovery chiller switches to leaving chilled water temperature. Since the chiller has switched from leaving condenser control to leaving evaporator control, other means are needed to maintain the hot fluid temperature. So, at the same time, the three-way bypass valve is controlled to maintain the heat recovery condenser leaving temperature. As the leaving hot fluid temperature drops, divert flow to the tower to increase that leaving temperature. By diverting condenser flow that would have passed through the upstream chiller's standard condenser, more of the unit heat is directed into the heat recovery condenser, and the hot fluid temperature is maintained, enabling control of both hot and cold fluid temperatures. To summarize, historically, we've been accustomed to chillers operating to maintain a chilled water supply set point. Heat recovery supply temperature control can be achieved by modulating tower return temperature or flow rate. Today's heat recovery chillers may control to a leaving hot fluid temperature, in which case the cooling supply fluid temperature is controlled through modulation of condenser flow or entering fluid temperature. In fact, Trane chillers can dynamically switch between the two. The options for heat recovery chiller condenser configurations enable some heat to be rejected when it's not all needed by the loads. This enables the designer to choose the relevant equipment and control scheme based on project requirements. Now that we know how to control heat recovery, Ben will walk us through places to find heat.
When heat recovery is used, the waste heat from chilled water loads is used as a source of heat for heating loads. This is an optimal arrangement as long as the system is cooling dominant. Cooling dominant systems have an overall surplus of heat. Any heat that's not used for heating loads must be rejected to a cooling tower or another heat sink. In heating dominant systems, however, the waste heat from chilled water loads is not enough for the heat recovery unit to satisfy heating loads. Additional sources of heat must be added. If additional heat is not added to the system, then one of two things will happen. Either the hot water loop will be underheated, meaning that the hot water set point is not met, or the chilled water loop will be overcooled, potentially causing low temperature cutout. Previous ENLs have discussed several different sources of heat that are available. In this section, we'll walk through some controls consideration for each of these sources of heat. When heat is pulled from ambient air, defrost operation may be needed. We'll review how defrost works and how it affects the hot water supply temperature. Phase change thermal energy storage, bodies of water, and geothermal may all require low temperatures to extract heat. We'll talk about how to control the amount of heat that's extracted. Wastewater or exhaust air heat exchangers can be used as either a heat source or a heat sink. We'll talk about how to use these in systems that switch between heating dominant and cooling dominant modes. When air-to-water heat pumps operate in an ambient temperature of 47 degrees or lower, the coil surface temperature may be at or below freezing temperature. Humidity in the air can collect and freeze on the coil surface, causing a layer of frost and degrading the coil performance. When visualizing defrost, think about a thin layer of frost, like frost on a window. Images of heat pumps covered in snow and ice are not a good representation of defrost operation. When defrost is initiated, the heat pump refrigerant cycle is reversed. Instead of cold evaporator refrigerant flowing through the coil, now we have warm condenser refrigerant. This heats up the coil surface and melts the frost. As the frost melts, water drips down the coil surface and collects in drain pans. If drain pans are not installed, the water could collect at the base of the unit and refreeze, causing a potential slip hazard. Now that we have an idea of what defrost looks like on the outside of the unit, let's think about what happens to the hot water loop. On a chart of cumulative BTUs versus time, a heating load is represented by a line with slope BTUs per hour. Since this is a cumulative plot, the line could go on into infinity, so we have to think about this as a snapshot in time. Before defrost happens, the heat pump capacity is modulated to match the heating load value. When defrost is initiated and the refrigerant cycle is reversed, the heat pump temporarily acts like a chiller, cooling the hot water loop and heating the outdoor coil. On that chart of BTUs versus time, this is represented with a negative slope. A typical defrost time is about 5 minutes long. After defrost, the heating loop has a deficit of BTUs, and the heat pump must operate with extra capacity to catch back up. Defrost recovery time depends on how much extra capacity is available and how much of a BTU deficit was accumulated during the defrost time. When sizing heat pumps, the defrost D rating is what gives heat pumps the extra capacity needed to recover from defrost. When the loop temperature is fully recovered, unit capacity again modulates back to the heating load value. Eventually, frost accumulates on the coil surface again, and the whole process repeats. The time between defrost cycles can be referred to as the defrost interval. An important design consideration for air-to-water heat pumps is the hot water loop volume or loop time. Ensure that the hot water loop time is longer than the defrost time. This avoids heating fluid getting a second pass through the heat pump while it's still in defrost mode. Features such as defrost delay time allow the system controller to bring on another source of heat before defrost is initiated. Defrost delay time may also be used to prevent multiple units going into defrost at the same time. Now let's talk about using sources of heat that operate with relatively low fluid temperatures. Water-based phase change thermal energy storage has a fixed temperature of 32 degrees. Geothermal and bodies of water may experience similar temperatures at the end of a heating season. To extract heat from a 32-degree source, we need to pump fluid through that source that's colder than 32 degrees. For example, we might pump 25-degree fluid into a thermal energy storage tank and get 31-degree fluid back. That gives us 6 degrees worth of heat. The question is, how do we control the amount of heat that's extracted? In this example, we want to control the hot water temperature. A temperature sensor is installed in the leaving condenser pipe of the water-to-water heat pump. The action device is heat pump capacity. Heat pump unit controls adjust the capacity as needed to regulate the hot water temperature. We can see that the evaporator leaving fluid temperature is not directly controlled. Instead, the evaporator loop temperature floats up and down as needed to extract sufficient heat from the source. To further illustrate this point, let's consider seasonal operation of a geothermal system. In the early fall, geothermal ground heat exchangers still hold all of the heat that was rejected from summer cooling. Return temperatures may be a balmy 78 degrees. As the heating season goes on and more heat is extracted from the earth, the ground temperatures drift downward. The evaporator loop temperatures naturally follow the ground temperature as they drift down. At the end of the heating season, thermal energy in the ground is depleted, and the evaporator operating temperature can be very low. This example illustrates the importance of knowing a range of expected ground temperatures to make proper heat pump selections. And conversely, heat pump temperature ratings must be known in order to size the ground heat exchanger. Now let's shift gears and talk about wastewater heat exchangers and exhaust heat recovery coils. These sources of recovered heat may be used to balance out the loads in a heating and cooling system allowing control of both the chilled water and the hot water temperature. In a heating dominant system where the heat pump unit controller regulates hot water temperature, the chilled water loop may be overcooled. In this example, the heat pump evaporator produces 35-degree fluid when we want to maintain 42-degree chilled water temperature. Recovered heat from the wastewater or exhaust air can be added to the chilled water loop and then modulated to control the chilled water supply temperature. The more heating dominant that the system is, the more recovered heat must be added. As the system becomes less heating dominant, the amount of external heat is modulated down. Eventually, no external heat is needed, and the chilled water temperatures may drift upward. This indicates a shift from heating dominant to cooling dominant conditions. In a cooling dominant system, we need to reject excess heat to maintain temperature. One option is to pipe the wastewater or exhaust heat recovery coils to the heating loop so they can be used as a heat sink. Systems that operate in both heating dominant and cooling dominant modes may include valves to switch between heat recovery and heat rejection. Once the valves are switched into heat rejection mode, we've got another choice to make. What should control hot water temperature and what should control chilled water temperature? One option is to leave the controller assignments the same as in heating dominant mode, meaning that the heat pump controls hot water temperature and the heat rejection capacity trims the chilled water temperature. This might be a little confusing because the heat rejection device is no longer hooked up to the chilled water loop. But as the heat rejection capacity is changed, the heat pump capacity will respond to maintain hot water temperature, resulting in chilled water temperature change. This is an indirect or cascaded type of control. Another option is to switch the control assignments for cooling dominant mode. Now the heat pump controls chilled water temperature and the heat rejection capacity maintains heating loop temperature. This is a more direct method of control and may improve temperature regulation. Not to mention that operators may find it more intuitive. The trade-off is that system sequences of operation get more complicated and the equipment must be capable of switching control modes. Whenever the system includes different operating modes, and especially if the controller assignments are changed in each mode, then it makes sense to create a mode table. A table like this may help to avoid missing sensors or modes where critical set points are not regulated. As the project matures, the controls engineer will incorporate this information into the system sequences of operation.
Thank you, Ben. It's good to see all of the possible heat sources and their impact on heat pump plant control. Modular chillers and heat pumps have become a popular option due to their flexibility and scalability. Ben, would you take us through the control of modular heat pumps and compare their control to the operation of packaged heat pumps?
Sure thing. First off, there's a 2023 Engineers Newsletter Live that covers modular chiller plant design, so we can build on what was presented there. For anyone who hasn't watched that ENL on modular chillers, let's recap some key ideas. Each module consists of compressors, heat exchangers, pipes, and valves, everything necessary to either heat or cool fluid. Modular units are available in air-to-water or water-to-water configurations. They can be used for cooling, heating, or both. Notice that there are two different configurations that provide both heating and cooling. We'll get into that shortly. Modules are combined into a bank. The number of modules in a bank determines the overall capacity and the number of unloading steps that are available. Capacity modulation is achieved by cycling compressors on and off. Each module has two compressors. When both compressors are running, full design delta T is achieved. When one compressor is running, half the design delta T is achieved. And when no compressors are running, the flow control valves may be closed to achieve flow turndown in the bank. Modular banks have more compressors and therefore more steps of capacity modulation. This example shows 3 of 8 compressors running. The leaving fluid from the first 2 modules mix to create the bank leaving fluid temperature. The last 2 modules are off and flow control valves are closed. Each module has a local controller that energizes compressors, actuates valves, and monitors for fault conditions. The bank controller determines how many compressors are needed to achieve the hot water set point. The bank controller also provides a single point of communication for the BAS or system controller. Now that we've reviewed operation of modular units as a chiller or heat pump, now let's consider operation of heat recovery and multi-pipe modular units. Heat recovery modular units are water-to-water devices that can control hot water or chilled water temperature, but not both at the same time. In this example, the unit is set up to control chilled water temperature. Although the chilled water set point is met, the hot water loop needs more capacity. The irony of this situation is that we're only running half of the compressors. Wouldn't it be nice if we can run some more of those remaining compressors to help out with the heating loop? That's where multi-pipe units come into play. Multi-pipe units have an additional circuit that can be used as a heat source or a heat sink depending on conditions. Now we can energize those last 2 compressors in heating mode and bring the hot water loop up to temperature without overcooling the chilled water loop. The additional circuit can also be a water loop. This is commonly referred to as a 6-pipe modular unit, and it's a great choice for geothermal applications. Let's break down the control sequence for multi-pipe units. As long as there are simultaneous heating and cooling loads, the controls will always start in heat recovery mode. This is the most efficient mode of operation. Unit controls will continue to add heat recovery capacity until the heating set point or the cooling set point is met. The first set point to be met is the smaller of the 2 values and represents the non-dominant load. Then additional capacity is added in either heating only or cooling only mode until the larger load value is met, the dominant load. Multi-pipe modular units are simple to apply in 4-pipe heating and cooling systems. The controls for hot water and chilled water temperature are built into the unit controls, and the system operates with high efficiency due to the heat recovery function. External changeover valves or valve control may not be needed because the changeover between heating and cooling mode is handled inside the unit. Some call this the easy button for heating cooling systems. The trade-off is that modular units can come with a cost premium. Similar function can be achieved with packaged heat pumps and changeover valves. If heat recovery function is needed, we can add a dedicated heat recovery unit. In many cases, the heat recovery capacity is small compared to the system capacity because it's limited to the simultaneous heating and cooling load value. This system is likely to have a lower equipment cost, but the trade-off is that more controls design and engineering effort is required. Before wrapping up this section, let's recap the heat recovery and multi-pipe modular units. Heat recovery units are water-to-water devices and can control either the hot water temperature or the chilled water temperature. Heat recovery units are high efficiency because the same power input provides both heating and cooling output. Multi-pipe units also provide heat recovery, but allow for regulation of hot water temperature and chilled water temperature at the same time. Multi-pipe units simplify system design by reducing external changeover valves and control devices. Packaged heat pumps can provide the same heating, cooling, and heat recovery function with a lower equipment cost. engineers must consider the trade-offs between equipment cost and system design complexity. Scott, we covered a lot of ground in this program. Would you recap today's discussion?
Sure, Ben. Let's start with the basics. Each controlled variable must have four things: set point, measurement, action, and controller. This is especially important when using a heat pump to provide chilled water and hot water simultaneously. Both controlled temperatures need those four things. Once the chiller's controlling temperature is determined, the other temperature must be controlled through other means. We've shown several plant configurations that are capable of meeting both temperatures with traditional condensers as well as dual condenser units. Dual condensers allow a degree of flexibility without requiring additional heat exchangers and space in the mechanical room. Heat pumps move heat from one temperature to a higher one. They do not create heat. This means that they require an evaporator load or heat source in order to operate. Ambient air is a readily available heat source for many projects, but will often require defrost. Consider how defrost will impact heat pump sizing and how controls can mitigate the impact on hot water supply temperature. When multiple heat sources are used in a project, create an operating table and prioritize the more efficient heat sources. For small to medium-sized buildings, modular chillers can simplify chilled and hot water control by packaging the majority of the controls within the unit. However, this can come at a cost, quite literally, since they are often more expensive than packaged heat pumps. For projects looking to lower first costs, consider combining modular heat pumps with packaged units. Last, for medium to large plants, combining centrifugal and positive displacement compressor types can optimize plant turndown and control. Jeannie, let's wrap this up.
Thanks, Scott. So that's our Controlling Hydronic Heating Systems program. We hope you found the information helpful. Please fill out a survey and let us know what you think of today's program. As always, the bibliography included in the handout provides more information on where to find a number of resources related to today's program, including the engineer's newsletter on this topic, all available and free 24/7. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses in the Trane Education Center. And finally, for those of you viewing in person, please ask your local host about details for upcoming Engineers Newsletter Live programs, or check them out at trane.com/ENL. And we launched a new podcast early this year, so please check out Cool Air Hot Takes and subscribe. Thanks for joining us today. We look forward to seeing you next time.